Hello, Earth Science students. If you chose this assignment for your choice board, here is what you need to do. First things first, you need to print out this copy of this chart. This is what we're going to be taking notes on. If you don't have access to a printer, you can easily just organize the information onto a separate piece of paper or draw up the boxes yourself. You don't necessarily need to print this, but it makes it a lot easier to print this. The other things you will need is something to write with, as well as some colors. I have too many here, actually. Probably won't use these ones because I have markers over here. But some colors, we're going to be using brown for the earth. Some things I want to stand out is going to be in purple, blue for the ocean, and red for mantle stuff, mantle convection. Um, yeah, so here we go. We're going to talk about plate boundaries. And most importantly, we're going to talk about how mantle convection leads to the movement of plate boundaries and what geologic features you're going to see from that. So the first thing I want you guys to write on your paper, obviously put your name at the top, but we're going to put an essential question on here. So go ahead and write EQ. And our essential question for today is, how does mantle convection influence tectonic plates to move? And how does that movement result in certain geologic features? Okay, there it is, our essential question. Let me get this a little bit closer so you guys can see that. So, how does mantle convection influence tectonic plates to move, and how does that movement result in certain geologic features? So, obviously, this is stuff that you guys have definitely seen before. You learned about tectonic plate movement and the certain plate boundaries in middle school, but we're going to go a little bit more in depth and kind of connect it all to what you guys saw with convection and again certain geologic features that come about from that. Okay, so the first of all, we have three major plate boundaries. We have convergent boundary, divergent boundary, and transform boundary. And you guys should be familiar with how those plates move. So when you have two plates that are converging, that means they're coming together. So we can just put a symbol over here. I'm using purple for this. Two arrows pointing inwards at each other to indicate that they're moving towards each other. Divergent boundary, it's the opposite. They're moving away from each other. So we can have two arrows facing away from each other. And then transform boundary is they're kind of sliding past each other. One's kind of going one way and the other is going the other way. So we're going to have arrows going opposite directions next to each other. Okay, so far, so good. We're going to start with convergent boundary. And so what we're going to do is for each one of these boundaries, we're going to draw a picture that kind of shows, again, the geologic features, what's happening with convection in the mantle, which direction those convection currents are moving. We're going to talk about the age of the crust, because that's gonna differ depending on whether we're talking about convergent boundary, divergent. We're going to start talking about earthquakes, deep versus shallow earthquakes, if we're going to see a lot of earthquakes or minimal. Volcanoes, topographic features are things that, like, are you going to get mountains or trenches or things like that? And then I'm going to give a couple of examples of each one of these. So first off, there's actually three types of convergent boundaries. There's oceanic continental, continental continental, and then oceanic oceanic. I've removed oceanic oceanic because it's very much the same as oceanic continental. You can just kind of substitute continental with oceanic and you'll have the same features. But the first thing I want to do is I want to draw what's happening to the crust when you have oceanic crust converging with continental crust. So we're going to draw crust. So this is going to be the oceanic crust. I'm actually going to have it kind of dipping down. You guys can kind of imagine this is like Bob Ross. I'm telling you guys how to paint, and then you guys follow what I'm doing. So we have oceanic crust here, and then our continental crust kind of goes like this. And just to make sure that we know that this is oceanic crust on the left side, let's put some ocean above it in blue. And just to reiterate, we have in terms of the direction that these plates are going, the oceanic crust is going this way, and the continental crust is converging, coming this way. So the question is what actually causes these plates to converge together? We have to talk about what's happening in the mantle. So remember that with mantle convection, the cooler stuff or the warmer stuff rises up and the colder stuff sinks down, and that causes these circular motions. So to make the plate, this oceanic plate, move towards the right, it's got to kind of follow the path of the convection current. So I'm going to draw a red arrow kind of going like that and circling back around like this. And then on this side, it's going to be the opposite. The arrow is going to be dragging the crust on the top in the other direction. I'm going to come back this way. So they should be converging towards the middle, sinking back down where it's cooler, and then it warms back up and rises back up towards the top. So that's how the mantle convection works. And I'm just going to kind of shade this in to show that we are in the mantle down here. Okay. The other thing is, so what's happening when we have two crusts that are coming together? If there's a difference in density, one is going to go underneath the other. We know that if something is more dense, it's going to go underneath something that's less dense. The less dense stuff is going to rise, the more dense stuff is going to sink. And that's what we see in the mantle convection. Remember, if it's less dense, it's going to go up. If it's more dense, it's going to go down. So that's the same principle that we see happening with the crust. And so what I want you to write is that the oceanic crust, the stuff that with the ocean on top, is going to be more dense. I'm going to draw an arrow pointing towards that crust. And then this crust is going to be less dense. And the reason why it's either more dense or less dense, it could have to do with the composition. If it has more iron in it, iron is pretty heavy. It tends to be more dense. Whenever you have ocean above it, that's really heavy. It's kind of pushing down on it. It makes it thin. If it's more thin, it's taking up less space for the amount of mass that it has, and that means it's more dense. So if it's more dense, it's going to sink under the other one. We call that subduction. So I'm going to write subduction right here. I have an arrow pointing straight up at where it's kind of going under. Let's take a look at what that looks like so far. So your picture should kind of look like that. So we have subduction, and what happens is as it's subducting, it as it's going into the mantle, it gets destroyed, it heats up, it melts, and that melting, I'm going to draw some red here because that's kind of melting, and that's going to rise up onto this side of the continental crust. And as that magma rises, it's going to start pushing that crust upwards. And now look what we have. We have some volcanoes. So whenever you have oceanic and continental crust converging, subduction is going to cause melting underneath, and that melting is going to rise up towards the surface, push the lithosphere or the crust upwards, forming volcanoes, and you're going to have volcanic activity. A lot of times we'll see volcanic arcs, long ranges of volcanoes. The other thing that you'll notice, and it might be kind of hard to see in my drawing, is there's actually kind of a little downward indentation right here in the ocean. That is a trench, an oceanic trench. So we're going to say oceanic trench. I'm going to point right down there. So that's another feature that you're going to see when you have convergence of oceanic and continental. So again, you're going to see subduction. Right at the where the plates are converging, you're going to see an oceanic trench. I'm going to put that a little closer so you can see it. You're going to see an oceanic trench right there. And on the continents, you're going to see a range of volcanoes. What else do I want to add to this? I think that's good. It's a pretty good picture. The only difference, remember I told you that you could have oceanic. The only difference is that this other one is going to be, in that scenario, this one's going to also be oceanic. And instead of having the volcanoes on land, you're going to have a chain of islands, a chain of volcanic islands. Okay, let's talk about the age of the crust. So whenever you have convergence at any point, this tends to be old rock. And so we'll say old ocean rock. subducts, and melts, like what we drew in the picture, and becomes part of the mantle. And you can kind of consider this like the end of the rock's life at that point. It gets destroyed there, so we'll write destruction. That says destruction, trust me. So we have old ocean rock subducts, melts, and becomes part of the mantle, destruction. So next we have earthquakes. So what happens is as this is subducting, it's not super smooth. It's not like it just slides like butter underneath the continental crust. It's going to get stuck and build up tension as that plate is trying to keep moving. And so what you're going to get is as this is subducting, this plate kind of gets stuck and it starts bending like this. And then eventually, so much pressure is built up that it's going to release. And you're going to get earthquakes and the possibility of tsunamis as well because it's pushing up all that ocean water above that trench. So we tend to get many earthquakes. But the biggest thing is whenever we have subduction, because it's going deep into the mantle, we're going to have deep earthquakes as opposed to shallow earthquakes. Deep. Okay, in terms of volcanoes, we drew a lovely volcano here, and like I said, we're probably going to see what's called an arc of volcanoes. And the important thing is this is actually going to happen to the side of the boundary. Like we drew in this picture, the volcanoes are off to the side because that's where underneath the subduction is kind of pushing upwards. So this is going to be to the side of boundary. Arc of volcanoes to the side of boundary. Next, topographic features. Again, topographic features are the things that we're going to be able to see, like elevation changes, that kind of stuff. So again, we see a trench. We're going to see an arc of volcanoes. Again, that's another topographic feature because we're going to see elevation change. And sometimes if we're talking about oceanic convergence, that's going to be, we could be getting island arcs, islands. Cool. And then some examples. The Andes Mountains are a good example of where we have oceanic and continental crust converging. I'm going to show you guys on this map right here. So the Andes Mountains are right along Chile right here. You can see the high elevation of these mountains. These are volcanic. And we have convergence of this oceanic crust and this continental crust. And what might be kind of hard to see is right in the water, you can see that dark shadow in the water. That's the oceanic trench because of the subduction zone right there. The other example that's where we see the deepest trench is the Mariana Trench. And that one's actually a convergence of oceanic and oceanic, but the same principles apply. This is where the convergence happens right here, and this is where we have the deepest part of the ocean. Okay, so that is oceanic continental convergence. Let's move on to continental continental. So this one, instead of having oceanic crust converging continental crust, we're going to draw continental crust converging with continental. But this one's going to be a little bit different. Remember that because oceanic crust and continental crust has different densities, we get a lot of subduction. But if it's continental and continental, we tend to not see as much of density differences. So instead of one really subducting under the other, they kind of just crash into each other and then shoot upwards. So I'm going to draw kind of this happening. So we have, actually, I'll keep the brown. Remember, convergence, they're coming together. So we see that it's coming together and it's kind of pushing upwards right in the middle. Typically, we do have a little bit of subduction. These tend to not be like the exact same density, so there might be like a little bit of subduction kind of going down underneath there, but maybe not enough to actually like cause a lot of volcanic activity. Again, we're going to draw our convection currents. These are basically the same as what we see over here because they're causing it to converge. There's the mantle. So a lot easier drawing for this one. And again, we're going to, because there's a lack of subduction or very minimal, we can say, I'm going to put a little asterisk here that says same density. And it's not going to be perfectly the same density, but certainly much closer in density compared to oceanic continental. So let's talk about the age. So again, whenever we see a convergent boundary, doesn't matter whether it's oceanic continental or continental continental, it's still going to be old rock. Old rock. And instead of, remember that we were saying in this one, it was being destroyed because it was going into the mantle and melting. It's still being destroyed over here, but in a different way. So old rock erodes because as it collides and rises upwards, it's going to be more subjected to high winds and things like that, and more weather. And so we're going to have more erosion at the top, and that's where that rock is going to be destroyed. So old rock erodes, becomes sediment. And it's still considered destruction of the crust. Okay, and earthquakes. Um, like I said, one of the things that leads to a lot of the earthquakes here is that subduction, and as it's subducting, it kind of gets stuck and then releases that pressure. Since we don't have as much subduction here, we tend to not see as many earthquakes, so we'll say there's some. And again, the thing that caused the deep earthquakes here was it's subducting deep into the mantle. Less subduction here, so we're going to actually see some more shallow earthquakes, especially if that rock is kind of shooting upwards. It's definitely going to be more shallow. Okay. And in terms of volcanoes, like I said, the thing that causes volcanoes is that subduction, and it melts in the mantle and then rises upwards and pushes that crust up. Because we don't have as much subduction, we tend to see some, maybe very few volcanoes. So we'll say some to few. Topographic features, we see a lot of uplifting, and that's that crust pushing upwards. And this results in really tall mountains. So the tallest mountains in the world are a result of continental convergence. We're talking about the Himalayas. So the Himalayas have, I think, out of like the 13 tallest mountains in the world, 10 of them exist in the Himalayas. We're talking like Mount Everest and K2 and those mountains. And on this topographic map, which shows differences in elevation, the Himalayas are right here, and you can see how much higher those mountains are compared to any other spot on the earth. The Andes are pretty high as well. But basically, you have convergence of what's India into the rest of Asia, and that shoots that crust upwards. Okay, so that's all of convergent boundaries. Next, we're going to talk about divergent boundaries. So instead of the crust coming together, now they're splitting apart. So we're going to draw crust like this, and I'm actually going to have it kind of a little bit higher in the middle, just like that. And again, let's remind ourselves that this is going in opposite directions now. Instead of coming together, they're pulling away from each other. So what is happening in the mantle to cause the crust to pull away? Let's look at the convection currents. So now, remember, these convection currents are going to influence the direction that the crust is moving, so they have to go this way, just like that. Now the interesting thing is as that crust moves away from each other, And this mantle, because of mantle convection, this magma is actually rising upwards. It's actually going to start coming up through the crust up here. And as it does, it's going to maybe actually breach the surface. A lot of the times it cools and solidifies before it actually reaches the surface. Um, and so it's not like just like an open chasm of hellfire where you've got just magma pouring out. There are some locations where magma does come up to the surface, but a lot of it um, cools and solidifies. And that's the reason why we see it's a little bit higher on these sides, is because as it cools and solidifies, it builds up. And that's what we call what is it called? A mid-ocean ridge or rift valley. But it forms a ridge a lot of the times. And what I would like you guys to add to this, I don't know what color I want to use. I'll just write normal pen. Right here, because we have magma coming up, cooling and solidifying, that actually creates new crust. So we have new crust right at the boundary. And then we have, as we go further and further away, it's older and older and older. So we'll have old crust or older crust this way. And like I said, right here, we're going to have a ridge. Now, ridge. I don't want you guys to think like these two drawings look pretty similar, but this ridge is going to be a lot not certainly not as steep or as high as what you're going to see in continental convergence. Um, but yeah, so these are the features that you guys are going to see. For the age, like I said, we're going to see new rock being made here. Right at the boundary is new rock. And that's made as magma cools. In terms of earthquakes, um, because stuff is coming up towards the surface and there's a lot of stuff happening right here, we tend to see shallow earthquakes and a lot of them. And actually, you might be wondering, how is it actually like with these ones we can easily tell why earthquakes are being made there because the crust is crashing into it or it's sliding past it. But here they're pulling apart. So the question is there actually crust sliding past each other? And the answer is yes. A lot of the divergent boundaries have these sections of mini transform faults all over the divergent boundary. I don't have a. Actually, I'll show you a picture after we go over transform boundary of what that looks like. Um, or when I'm showing you examples, I'll show you where those little transform faults are. And those are as you have the sliding of the faults or the crust, you're going to have earthquakes, the chance of earthquakes there. But it's going to be really shallow, like I said. Next, let's talk about volcanoes. We're going to have few volcanoes. Like I said, most of the time the magma is going to cool and solidify before it actually reaches the very surface. Um, and these are going to be found right on the boundary line. And this is an important distinction because if you noticed over here, the volcano's off to the side, it's not on the boundary line. These ones, the volcanoes are going to be right on the boundary line. Topographic features, we're going to have mid-ocean ridges. And that's if this divergent boundary is happening underwater, then we're going to have mid-ocean ridges. And most of the divergent boundaries are in oceans, so we tend to mostly see mid-ocean ridges. If they happen on land, we get rift valleys. I'll show you a picture of that. So our two examples, we have the Great Mid-Atlantic Ridge. And then on land, we have the Great Rift Valley in Africa. Okay, let's take a look. So, in terms of the mid ocean or the mid Atlantic ridge, you can see, so this is the Atlantic Ocean, and you can see what kind of looks like a zipper going right down the middle of it. This is the divergent boundary that exists in the Atlantic Ocean. And actually, what you're seeing is that slightly higher elevation of the ridge. And that's right at the boundary. You see the crust is a little bit higher because it's building up as that magma cools and solidifies, it builds up. And so we see slightly higher elevation all the way along there. And then for the uh, Great Rift Valley in Africa, there's a divergent boundary that's actually splitting this continent apart. And you can see it's the Red Sea right here is a divergent boundary. And a little bit of it kind of sneaks into Africa. And there's this, it looks kind of like a scar right through Africa. So that's that Great Rift Valley. And as whenever you have a divergent boundary on land, as it's splitting apart, it's going to get to the point where water's going to fill it up. And now you've got a new sea and eventually maybe a new ocean. Okay, so that's divergent boundary. And the last one, we have transform boundary. And this one, if you're super artistic and good at drawing three-dimensional things, you can try your best to copy what I'm what I'm drawing here, because I'm going to draw three-dimensional. So remember, transform boundary is they're sliding past each other. So I'm going to draw one crust. Here's my three-dimensional creation here. So there's one crust. Here's the other one. Okay, so there's our two crusts. This one is going one way. This one's going the other way. So now it's really interesting what's happening in the mantle to cause these to go in opposite directions. Underneath this one, remember it has to follow the direction of the convection underneath. So the top of it is going to go to the left. Over here, this one's going to go in the opposite direction, like that. Now, this one might look very similar to what we see here, but it's not. So instead of it going like this, that's divergent. Transform is they're going this way. It's kind of hard. It's one of those things you try and like pat your head and rub your belly at the same time, but they're basically going in opposite directions at the top and the bottom of the motion. But that's what leads to transform boundaries. And again, they're sliding past each other. So in terms of the age, it's not really a place where we have destruction. Oh, I forgot to add. For these ones, we said that these were destruction. Over here, construction. It's constructing new rock. This one is not really doing either. It's kind of just moving around existing rock. In terms of earthquakes, again, whenever you have something sliding past and grinding past, it has the possibility of getting stuck. And when it gets stuck, it's going to build up pressure and then eventually release. And with transform boundaries, we tend to see many earthquakes. But because there's no subduction, we tend to see shallow earthquakes. Volcanoes, minimal, none to few. Because remember, what causes volcanoes is either subduction, like we see over here, or actual magma that's coming up because the convection cycles are kind of pushing magma up through the crust. This one has neither of that, so we don't see really any volcanic activity. Topographic features, we're going to tend to see some hills and small mountains. So none of the crazy, like huge, like Mount Everest or crazy trenches like we see in the previous ones. And the reason why we get some mountains is because, again, these don't slide perfectly past each other. We tend to see that, like, let's say this was the actual crust, this piece of paper. If I try moving this side this way and this side this way, it tends to start crinkling it up. And that's what kind of causes some of these hills and stuff. But they're not going to be super tall. And then some examples. The greatest example is the one here in California. That's the San Andreas Fault. We know it's pretty prolific at its creation of earthquakes, San Andreas Fault. And so that is going to be right here, California. It's one of the only places in the world that has transform boundary. Okay, so something that you guys should know, again, in the future, you guys will have to be able to identify based on certain topographic features, earthquake data, volcano data, what type of boundary you might be taking a look at. Before you guys finish with this, what you need to do is on the back side, you flip this over, you're going to write your summary. And there's a couple of things you need to include in your summary. First thing is you need to answer the essential question, which is this guy right at the top, EQ. So answer the essential question, and then just summarize the important information. And what I would say in terms of important information, how do you know what's important? Pretty much all of this is important. I would recommend, and actually this is a requirement, you guys should go through and underline things that you feel are the most important things or the things that you think are going to be the easiest pieces of data that you might use if you're trying to identify a plate boundary. So it might be really easy to see an oceanic trench, or it might be really easy to see a mid-ocean ridge, or the fact that it has many deep earthquakes might be something that would be really easy to see. So go ahead and in any color, you're going to underline the most important bits of information, and that would be something that I would want you to summarize as important information in your summary. Okay, awesome. Thanks guys for watching.